Okay, so I was defining, so previous slide was this one, was defining this various type of analysis, and now that we have defined all these concepts, I want to give you an example, again, this Bayesian inference. And as I told you, so if you look at all these items, data generation, protocol, blah, 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 you can have a Bayesian version of them. Doesn't mean that Bayesians would accept all of these as the definition of Bayesian inference, but these are Bayesian variation of all of them. So for the generation of the data, as I told you before, you can assume, you don't have to, but you can assume that the function is sampled from some prior and the data is sampled and labeled according to this function. You typically have some kind of offline protocol where all the examples are given, and then you want to build a function to predict the next examples. The loss measure is typically the expected error because you have a probability measure, so you can take the expectation under this probability measure. And the type of analysis also typically can be the average under the prior. That's why you make this assumption that the function is sampled from some prior. It's only for the analysis itself. And sometimes you have also other assumptions on how the labels are corrupted by noise. Okay, and of course you don't have to take all of them as the definition of Bayesian inference. And you can also make all sorts of combinations. So you can make an average case analysis in a setting where in a different protocol or with a different loss measure. So it's not there. I mean, there is no reason to see big distinctions. So you can combine all these things in different ways. But the important point is to see or to understand what you are combining and what it means to combine them. So in my case, I will be interested mainly in a worst case analysis because I want to provide guarantees that hold no matter what the problem that you are looking at is, and try to avoid assumptions as much as possible. And of course, under these conditions, look for the best algorithms. So the kind of quantity that I want to investigate is this one. So I have, say, predictor or learning algorithm. I have a problem. I can characterize the loss of this predictor on this problem. It can be a function that I cannot actually measure. It can be the expected error. But it's something that I can at least approximate. And I don't want to make assumption about what the problem is actually, because I don't know. I just have data. I don't know where this data comes from. So I take the maximum over all possible problems. And hopefully, I would like to have an algorithm that minimizes this quantity here. And the question is whether this is possible and reasonable. Unfortunately, stated like this, it's not really possible. We can show, and I'll give you examples of theorems that show that you cannot do that, or you can. This minimum will be always trivial. And the point is that you can always construct problems that will make your algorithm fail, no matter which algorithm that you are using. Okay. Now, again, it's a matter of point of view, but I think hopefully it will be the last time I talk about point of view, and then I get to actual formalizations. I think it's important to understand this distinction. So rewriting this quantity that I shown on the previous slide, there are several ways of looking at it. One way is the so-called minimax point of view. So the minimax point of view is to say, well, if this does not make sense when I take the maximum over all problems, then I can just restrict the class of problems that I'm allowed to consider, and then have a quantity that makes sense. Okay, it's perfectly fine to do that. I say I just rewrite the same thing, but now I restrict my problem to be in a certain class. So I make a certain number of assumptions on how the data is generated, how the noise behaves, how the how smooth my function is, and so on. And I say, well, given the worst such function or the worst such data, what is the best algorithm, or what is the algorithm that minimizes the worst error? Okay, and there are two versions. You can also consider this quantity here, where you subtract the best loss, so some kind of the best predictor that you could have obtained if you knew the problem entirely, right? And this is fine. We can, I mean, there is a whole domain of study, the minimax estimation theory, where you can prove results about such quantities. Another related point of view is the so-called learnability point of view, where, again, you assume that the function that you're trying to approximate, or your so-called target function, the function that has labeled the examples, belong to some class. And then the question is whether you can learn this class, and learning the class means being able to identify any of the functions in this class with enough examples. So given enough examples, you can construct an algorithm that will learn any function in this class, and which means that the minimax error that I showed previously will go to 0 when the sample size increases. Okay, and again, this means you make assumptions. You assume that your target function belongs to some class, or that your data is generated in a certain way. And if it's not the case, then your results do not hold anymore. So they are not useful anymore if this is not the case. And the problem is you can never, or almost never, be sure that your assumptions are correct. In practice, you cannot say whether the noise is Gaussian or not Gaussian. It is like it is. It's just you have no way to prove that the noise has a certain form. Another point of view, which is even worse in my opinion, is the so-called modal identification. So in this case, you don't want to minimize the error. You want to identify the function itself. So what you look at is the distance between the function constructed by your algorithm and the true function, if it exists. And usually you cannot define it, but fine. In certain cases, I mean, you can make statements that tell you that given a certain function, you can construct an algorithm that will have such and such distance, or produce functions that are at such and such distance from the true function. But again, you make assumptions, and you're trying to do something that is not useful in practice. You don't want to find the function in practice. You just want to make good predictions. So again, the point of view that I think more interesting is where you try to minimize the errors that you make, and not try to identify something that you actually don't know that whether it exists or not. I mean, is there any true function or not? You never know. So that's why I better think about this point of view, which I call competitive approach, or you can call it also it's sometimes called the regret approach, where what you do is you don't want to minimize. You find an algorithm that minimizes the error, the worst case error in a class. You allow all possible problems, but what you restrict is the set of comparisons algorithm. So you have, say, you have a set of functions or a set of algorithms. You look at the best such function for the problem at hand, and this gives you this quantity here. Now you compare this to the error that you make with your algorithm, and you want to build an algorithm that is such that under the worst possible problem will minimize this difference, or this is sometimes called the regret, because it means if I had known what was the problem, I would have chosen this reference, which is the best one. Maximizing minus the loss means minimizing the loss, right? So I would have chosen this reference, But I did not do it. I choose instead a predictor. So I'm a bit sad about it, not having chosen this one. And the sadness is measured, or the regret is measured by the difference in those two losses. Okay? And this way, I'm not making any assumptions about how the data is generated, where the target function lies, and so on. I'm just saying, well, how can I compare, or how do I compare with this class of functions? The thing is that often the results look like the same. So bounds on this kind of quantity are more or less the same as bounds on the minimax quantity of the previous slides if you take the maximum over the problems such that the target function is in the reference class. So if you have a set of functions and you look at the worst possible error when the target function is in this class, you obtain more or less the same result as if you compare, under the worst possible data generation, the loss of an algorithm with the loss of this function, of the functions in this class. So it's more or less a matter of taste, but I think it's important to interpret these kind of quantities in the right way. And I think this way is kind of going in the direction of avoiding as much as possible assumptions about what your problem is. And OK, of course, what you do once you have defined such quantities is to prove, upper and lower bounds. And OK, this explains how you would prove such bounds. To prove an upper bound, you take an algorithm and you want to prove a bound on the difference of the losses that is independent of the data generation mechanism, and that gives you an upper bound. And to prove a lower bound, you have to show that for every learning algorithm, you can exhibit or construct a data generation mechanism, or probability distribution, if you will, that will maximally mislead your algorithm. Anyway. OK, now some definition. So I will try now to formalize a little bit what I have said so far and give you definitions. And of course, by doing so, I will restrict myself to a specific setting. In this case, it will be the IID setting, not because I think IID is the right assumption, but it's just that it's convenient. And you can actually obtain the same, more or less the same result if you remove completely this IID assumption. So these are classical notation. X is the input space, Y is the output. Usually we take binary classification, so it's just 0 and 1. N is the sample size, number of training examples, which are of the form xi, yi. And L is the loss function that measures the distance between the predicted label and the true label. So usually it's just the indicator that the labels are not the same. Okay, so now with these notations, what I call the expected loss would be written like this: the expectation with respect to x and y of the loss between the predicted g of x and the true y. And the cumulated error would be, as I said before, the sum of the errors made at each prediction. So at each data point, you make a prediction and you compute the error, where in the online setting, at least, you would allow g to change as time goes. So as you get more instances, you would allow g to change. So it should be more gi written here. Okay. Another notation, I will use gn as to denote the function returned by my algorithm. So the small n will mean that my gn depends on the data, on a training set of data of size n. Okay. And you can, given the loss, defined in this or this way, you can define the optimal, or the function attaining the optimal loss by g star. Okay. So if you rewrite using this notation the quantities before, so in the case of modal identification, So what is in blue is what I consider, and these are the other possibilities which I don't consider. If you do modal identification, you are comparing Gn with, sorry, it should be G star here. And you have some kind of distance between those two functions, and you try to minimize it. Okay. Here we do risk minimization, so we try to minimize the loss. Sorry, it should be G here. What happens? Okay, so Gn. So yeah, it should mean over G of the loss. Okay. Then you have what I call the average case approach, where what you try to minimize is the sum over a certain set of possible distributions or possible generation mechanisms of the difference between the loss of your algorithm and the loss of the best one. The minimax approach, you take the maximum over this restricted set of probability distributions. And the regret approach, you take the maximum over all possible distributions, but you compare your loss with the loss of functions in the reference class, capital G. Okay? Does that make sense? Or is it fine? Okay. Okay, so this is a small technical point, but quite important. So when you consider such a quantity and you try to prove lower bounds, that's something that you may encounter sometimes. What you do is you construct, as I said before, a bad distribution. So given an algorithm, you construct a distribution that will make this algorithm make as many mistakes as possible. And you can construct this P in a way that depends on the sample size or not. So if you do it in a way that depends on the sample size, you obtain what is called a weak lower bound. And if the bad P does not depend on the sample size, you get a strong lower bound. And it's more interesting because usually the problem is fixed, so P is fixed, but what is not fixed is the sample size. You can get more instances of a given problem, and what you're interested in is whether when the problem is fixed and you get more instances, whether you will eventually be able to get a low value for this quantity or not. So strong lower bounds are more interesting. So I want to finish by giving you a few statements of kind of negative results in that setting. So once you have set all these notation, you can show several things which are called the no free lunch theorems. A simple one is the first, actually historically the first one from Wolpert. It says that if you take two different algorithms and if you take all possible problems, which means all possible data distributions. So to speak about all possible data distribution, in his case, is looking at a set at a finite domain. So the input space is a finite set, and you are looking at finite output space as well. So binary classification, for example, where your input is finite. So it's a bit restrictive, but in that case, you can show that if you take the average or the sum over all possible problems of the loss that you obtain on future instances, so on the instances that you have not used for training, only the test instances, and you have to ensure that they are different from the training instances. So if you do that, it will be the same quantity no matter which algorithm you consider. So all algorithms will, on average, behave in the same way. Or, put another way, if an algorithm is good on some problem, it will be bad on another problem. Or if it's better than, so if you take as a reference here a stupid algorithm that always predicts in the same way, if you have an algorithm which is better than this on some problem, then it will be worse than it's on some other problem. Okay? So in a way, it means that you cannot say my algorithm is better than some other algorithm. You can only say what my algorithm does, or the prior implemented by my algorithm is better in this specific class of problems, for example. Okay, so that's very important because in a way it tells that what we naturally would be tempted to think, which is, okay, these algorithms, support vector machines are better than neural networks, for example. This has no meaning. You cannot even give a mathematical content to this sentence, right? So you can only say SVMs are better than neural networks for this kind of problem. And this kind of problem has to be a kind of limited class of problems. In a way, it's kind of trivial, this theorem, if you think about it. So what it says essentially is that if you have no assumption, so if you allow all possible distributions, then of course there can be distributions, like if you have observed the value of the function at certain points, and you are asked the value of the function at other points, why should they be related in any way? Because there can be distributions for which these are related, but there can be distributions for which they are not related. And if you have a certain way of extrapolating from the training instances to the test instances, then you can take the probability distribution that assigns exactly the opposite labels to your test instances and create a very large error for your algorithm. So you can always kind of invert the labels of the future instances maliciously, in a way. Okay. So one way to go around this is to introduce the Iid assumptions, as I said before. So you assume that your data is generated independently from some unknown but fixed distribution. And this already implies that there will be a relationship between what you have observed and what you may observe in the future, right? Because they are sampled from the same distribution. So maybe I'll skip this. You have it in the slide. But I just want to get to the point before the end of this lecture. The good news is that under the Iid assumption, because there is a relationship between what you observe and what you will observe in the future, then you can construct algorithm that will be able to learn any function. So there are algorithms that, this is called universally consistent algorithm, that are such that with enough data, they will kind of correctly identify the target function, if you want. Okay? But the bad news is that even if such algorithm exists, then it does not buy you anything on finite samples. So there are two other versions of the North-Freeland theorem that tell you that not only for a finite sample, you can have arbitrarily bad error for any algorithm, even for a universally consistent algorithm. And even worse, and that's kind of the weak result versus strong result, you can construct a distribution such that for any given, so it's the other way around, given an algorithm, you can construct a distribution which is such that, of course, the error will converge to 0, because at least if you take a universally consistent algorithm, but this error will converge arbitrarily slowly to 0. Okay, so you will never be able to say whether you have a small error or whether you can get a smaller error if you have more data. Okay, so I think I'll stop here, and tomorrow we'll see more details about this. So if you have questions, feel free to ask.
I have one question. For me, it's always a problem. What is good model? What is bad model?
Yes.
An example: you have training data. You construct a model. You have for this training data, classification error is 0.
Yes.
Now I come up with the test data, and classification is almost 100 error.
Yes.
Is it a good model?
Well, actually, that's exactly the point. So tomorrow we'll see. I would say there are two components when you evaluate a model. Usually it's so we'll see it tomorrow, but usually you decompose the error into what is called approximation error and estimation error. So estimation error is how misleading your model might be, and it measures how far the error on the training data and the error on the test data can be.
But it's very far away. But for the training data, I have perfectly.
Okay, but that means your model is maybe too big, right? But it doesn't mean it's a bad model, because when the model is big enough, then you can approximate well the target function, generally. So it's kind of a trade-off between those two things. But the problem is the approximation error. So the fact that your model can capture the target function is something that you cannot prove, right? You cannot, because it would mean you have assumptions about what your target function is.
So does it mean that I had bad assumptions about my model?
Well, if it's such that you have a small training error and a large test error, it doesn't tell you anything about the assumptions. It just about the fact that your model captures or not the target function. It just tells you that your model is so big that you can overfit. And actually, that's the kind of thing that we will try to quantify.
Yeah, but I think it also means that my model doesn't fit well my actual data.
No. If you have zero error, it means that it fits perfectly. So it could be that the target function is inside your model, but what it really means is that it's too big, and it overfits.
It means that it trivially fits because it's so big that it will fit anything.
Yeah,
so
could be. Yeah.
If it trivially fits, then maybe in this sense you could say it doesn't fit.
I disagree with you.
Well.
Strongly, because if it fits everything, that would be random guessing. In this case, there's no random guessing; it's deterministic.
And that's always the problem.
No guessing. So it's
Yeah.
fitting good, guys.
I don't see what you mean. Because, I mean, if the model is big, you can fit a lot of things. So you can actually fit your data, your target function.
The problem is that you assume that a good model should fit data. What I'm telling to you, that there are cases where this is a wrong model, wrong theory.
No, I mean, at least it should fit the data in the sense that it minimizes the objective function that you have. So which means if your goal is to predict well in certain circumstances, like on average or in cumulated error sense or whatever, at least your model should allow you to get a low value for your objective function.
No, but you have the assumption that objective of a good model is minimizing error in some sense. What I'm saying to you that this is not capturing all situations. And I think it's no point in discussing this, and we can do it all.
Oh yeah, sure.
But is it a unique measure of goodness of your model?
Well, I mean, my point tomorrow will be that the only thing that we can say about a model is whether it will lead you to overfitting or not, in some sense. But we cannot say whether it will fit well or not. We just can quantify, in some sense, how far the error measured on the training data and the error measured on the test data might be when you use this model.
Because I think that in that case, maybe it's better to change the model in such case that I assume that my error on your training data is not more 100%, but 50%. So
yeah.
But,
in that case, it might be better to have a larger training error. So have a smaller model that ensures that you have a larger. And it's a trade-off. Yeah. Okay. But you cannot really, the theory cannot tell you anything about the trade-off itself. It can only tell you about the amount of overfitting that you may observe.